Greetings, welcome to lecture number 6 on basic circuit theory. I am Razavi. Today we will continue to look at node analysis and introduce a step-by-step procedure that allows us to solve any circuit. We saw a few steps last time. Today we will complete those steps. And then we'll go over a bunch of examples to hammer these ideas in. And in these examples we will begin to see a difficulty with respect to node analysis. And to resolve that difficulty, we will introduce the concept of supernode so that we can analyze any circuit. But before we go there, let's take a look at what we covered last time. In lecture number 5, we looked at various ways of simplifying a circuit by identifying familiar structures. For example, if we have voltage sources in series, then we can merge them into one, which is equal to the algebraic sum of these two voltage sources. So we just have to pay attention to these signs when we want to decide what voltage we should put here. Similarly, for current sources, if they are in parallel, they can be merged into one, which is equal to the sum of the two. So again, that's valuable because it simplifies the circuit. And finally, we have, for example, resistors in series or parallel, and they can be simplified to give us a more compact circuit. And then we started to look at the node analysis. So I introduced a couple of steps. So today we will go over node analysis more carefully and complete all of the steps that are necessary. Okay, so let's begin with node analysis steps. So we said that step number 1 is to select a reference node, which we also call the ground and denoted by GND. So suppose we have some general circuit, we have various devices and lots of nodes and so on, and we come along and select one node to be ground, to be the reference. Any node will do, so we can pick one node here. This is the symbol for ground, so we will use that from now on to indicate that this is our reference. And next, we assign voltages to these nodes. So step number 2 is assign voltages to all other nodes. So for example, I may say the voltage at this node is VA, the voltage at this node here is VB. And what that really means is that each of these voltages is measured with respect to ground. So when I say I have VA volts here, it means I put a voltmeter between this point and this point, and I measure VA volts. And I put a voltmeter between this point and this point, and I measure VB volts. So a voltage is always measured between 2 points. Okay, so that means that if I start out with a circuit that has n nodes, and I call one of them to be ground, then the remainder of the nodes will add up to n minus 1. So that means that we have n minus 1 voltages. These are voltages that we have assigned and are unknown at this point. So we need to find n minus 1 voltages, VA, VB, etc. Okay, so let's say that this whole circuit, when you started out, has n nodes, and now we have identified n minus 1 unknowns that we have to find. Okay, so in the next step, we will write the current through every branch. So step 3, write the current through every branch. And we really want to do this on the schematic, on the circuit itself, not separately. Okay, as we will see, it's important to do that. All right, so for example, I have a resistor here. Let's call that R1. And I would like to write the current flowing through this branch in terms of the voltages that I have assigned to the circuit. How do I write that? Let's go back to this lemma that I introduced last time, a few times ago. We saw that if we have a resistor and it has a voltage of V1 on this side and a voltage of V2 on this side, then the current going from left to right through the resistor is equal to the voltage on the left minus the voltage on the right divided by the resistor value. All right, so we always have to remember this. We solved the circuit before, and that was the conclusion that we arrived at. So we're going to use that conclusion here. Okay, so then how much is this current here through R1? Well, so the lemma tells us that the current to a resistor is given by the voltage on the left minus the voltage on the right divided by the resistor value if the current is going from left to right. So that would be VB minus VA over R1. Of course, if you would like to point this arrow to the left, then you would write the current as the voltage on the right minus the voltage on the left divided by the resistor. Either way is fine. Okay, so we will write the current through every branch in terms of these voltages. The reason we don't want to do this outside the circuit is that if you write it here, do you have a name for this current or not? If you don't have a name, it will be very confusing. If you have a name, you say, for example, I1 is equal to VB minus VA over R1, then that I1 looks like an unknown, and we don't want to introduce another unknown. So it's important to draw the circuit really big so that we can write all of these currents on the circuit without calling them new variables. All right, now we go to step number 4. Since I have all of the branch currents, I can write a KCL at every one of these nodes. So write a KCL at all nodes except at ground. Okay? All right, so let's make sure that we understand what's going on here. We will have n minus 1 nodes with voltages. So I can write n minus 1 KCLs at these nodes. So these will give me n minus 1 equations. N minus 1 equations. And I have n minus 1 unknowns, meaning these voltages. So if I have n minus 1 equations, independent equations, I can find the voltages. So that allows us to find the voltages. Why do we not write the KCL at the ground? Well, we can, but it's not an independent equation. How do we know that? Well, we know that we have only n minus 1 unknowns. So we need only n minus 1 equations to solve that. And that the n minus 1 equations are coming from these KCLs that we are writing at these n minus 1 nodes. So if I write a KCL at ground, it's just a linear combination of the other equations. So you don't really have n independent equations, we have only n minus 1 independent equations. All right? Okay, so you can see that by going through these 4 steps, we have been able to find all the voltages in terms of the known parameters of the circuit. And once we have the voltages, we can find anything else, right? If you want to find this current, that current would be this voltage minus this voltage divided by that resistor. So with this in mind, we're going to go over some examples just to get comfortable with the idea. So let's start with something simple. So here's a simple example. Okay, so I have a current source, which I'll call Ix, and then I have two resistors, three resistors. Okay, so we have three resistors here and here and here. So we call these R1, R2, and R3. Now I should draw the circuit a little bigger, but I'll try to squeeze everything in the circuit itself. Okay, so here's the circuit given to us, and we want to solve the circuit, meaning we want to find everything about it. And the question is, how do we do that? Well, let's go ahead and select a reference node. Where should that be? Any node will do. Maybe this node. You see, this node, this piece of wire connects three terminals. That's sort of the most crowded node. This is also the same, but why don't we pick this one? Pictorially speaking, graphically speaking, we would like the ground node to be on the bottom of the page because it helps us visualize things. It's not a must, but it's helpful. So let's try to call this node ground. It's important to understand that this is all just one node because this and this and this are connected by a piece of wire. A piece of wire does not have voltage drop on it. Remember, it's a short circuit. So these all have one node. Okay, so we went through step number one. Step number two, we will assign a voltage to every other node. So which nodes do we have? We have this one and this one. So let's call this something. So we can call that VA, and then this one VB. Remembering that VA means the voltage from here to here, and VB means the voltage from here to here. Okay, always with respect to ground. Okay, so in step number three, we will find the currents through all the branches and write them on the circuit, on the schematic. So let's try to do that. Let me change the color of my pen here to make sure that the currents stand out. Okay, so let's start from here. How much is the current flowing through R1? Well, the top voltage is VA, the bottom voltage is 0. So the current wants to go from high potential to low potential. Ohm's law says high potential minus low potential divided by the resistor value. Or if your head, if you turn this by 90 degrees, it looks like this, right? So on the left we have VA, on the right we have 0. So VA minus 0 divided by the resistor value. So this current is just VA over R1. Okay, that's great. Now, how about the current through R2? The current through R2 going from left to right is given by the voltage on the left minus the voltage on the right divided by the resistor. So that would be VA minus VB divided by R2. All right. What else? We have this branch. How much is the current through R3? For example, going this way. Well, again, the top voltage is VB. The bottom voltage is ground. So VB minus 0. VB is the voltage difference from here to here, right? So VB minus 0 divided by R3. So VB over R3. That's the current through R3. How about the current through this branch? Well, that's IX. IX is a current source. It wants to force that current, so it's known. We don't need to call it anything because we already have it. Okay, so we have completed step number 3. Now we go to step number 4 and write a KCL at all of the nodes that would accept the KCL or would give us meaningful information. Because we have 2 nodes besides the ground node, we will write only 2 KCLs. After all, we have only 2 unknowns, VA and VB. Okay, so let's do that. Let's write a KCL at this node, node A. How do we do that? Well, remember, one approach is to say all of the currents coming in must add up and be equal to all the currents that are going out. So which current is coming in? IX is coming in. So IX, I'm going to write 2 equations. So IX is equal to this current which is going out. So VA over R1. And this current which is going out, so plus VA minus VB over R2. So we wrote the KCL at one of the nodes based on all the branch currents that we have. Now you can see why it's useful to write the current equations on the schematic as opposed to separately. Because here it's very easy to see that this current is coming in, these two currents are going out. There's no room for mistakes. Okay, now let's move on to this node and again write a KCL here. We know that this current is coming into the node and this current is coming out of the node, so we just have to equate these two. So we say VA minus VB over R2 is equal to VB over R3. Okay, so now we have two equations and two unknowns, so we can find VA and VB. So from these two, we can find VA and VB. All right, so that's the procedure that we want to follow. Now, when we start out, you might be wondering, do I have to show this arrow going from left to right? No, it's entirely up to you. If you want to show the arrow going from right to left, that's okay too. You just have to remember how this equation works out, right? So if the current is as an arrow going from right to left, then that arrow, that current is equal to the voltage on the right minus the voltage on the left divided by the resistor. So long as you're careful about the signs, everything is fine. The math will tell us exactly what the currents will be actually at the end and which direction they are flowing in. Okay, so that's a simple example. Let's make things a little more interesting and go to this circuit here. So let's go to another example here. Okay, so I have a bunch of devices here. I have a current source. Let's call this IX. And let's see. And then I have a bunch of other devices. R1. I'll try to draw this big because we're going to need to write lots of current equations. R2. Then we have another one here, R3. Then we have a current source here, IY. And then we have a resistor from here to ground. Let's call that R4. And then we have another current source here. Let's call that IZ. Okay, so we have the circuit and we want to solve it. All right. So as long as you remember the steps of node analysis, everything is fine. So let's follow the steps. Step number 1, identify or select a reference node. Any node will do. For example, I'll pick this node here. So that will be my ground. So all other voltages will be measured with respect to ground. Okay, step number 2, assign voltages to all other nodes. So we just go around and give them names, right? So here, for example, I can call this VA or V1 or something, whatever you like. Call this VB, this node, and call this one VC. Again, this voltage is from here to here, is measured. There's a voltmeter that you put between these two nodes and you measure VA volts. This one is from here to here. This one is from here to here. That's all we have, right? There are no other nodes. Okay, so we have 3 unknowns. We need to write 3 KCLs. So we're going to go to step number 3 and find all the currents through the branches before we start writing our KCLs. All right, so it's good to make sure that every current is shown very clearly to avoid any mistakes. So let's start out with the current through R1. How much is this current here? Going from left to right. Again, same idea. going from left to right, is the voltage on the left minus the voltage on the right divided by the resistor value. So that's VA, this one minus this one, divided by R1. That's the current through R1. How much is the current through R4? This voltage minus this voltage divided by R4. So that would be VB over R4. How much is the current through this branch? That's known. That's IX. IX wants to push that current, so we don't need to write an equation. Similarly, this branch wants to carry IZ. So again, that's fixed, and we don't have to write a current there. Okay, how about the current through R2? Let's say going this way. So that would be this voltage minus this voltage divided by the resistor, right? Voltage on the left minus voltage on the right divided by the resistor. So I don't have room here, so I will write that over here, VB minus VC over R2. That's the current through R2 going from left to right. And finally, the current through R3, this current here. How much is this current? Well, this voltage minus this voltage divided by R3. Right? If you rotate by 90 degrees, voltage on the left minus voltage on the right divided by the resistor. So that would be VC over R3. Okay, so use different colors to make sure that we don't confuse various quantities. And now this circuit is ready for KCLs. That's our last step here, right? We write KCLs. So 2 unknowns, 2 KCLs. We write the KCL here. Sorry, 3 unknowns and 3 KCLs. So we have three unknowns, and we need to write 3 KCLs. Okay, we start from here. What does a KCL at that node look like? So I'm going to write 3 equations here. I have some currents coming in, some currents going out. We just have to write them out. So this current is coming into the node. This current is coming into the node. So I add those two, IX plus IZ, and I write that equal to this current which is going out. So that would be VA minus VB over R1. VA minus VB over R1. All right, that's great. Okay, we move on to the next node at VB, and we write a KCL here. We have this current coming in, and that's the only one that's coming in. So we write VA minus VB over R1 is equal to this coming in, this is going out, this is going out, and this is going out. So we just add all those 3. So that would be equal to IZ plus VB over R4 plus VB minus VC over R2. This one, that's the current going from this side to this side. All right, 2 equations. We need 1 more equation, and that would be the KCL at this node. So a current is coming in. This current is coming in equal to that value, and these 2 are going out. So we say VB minus VC over R2 coming in is equal to IY going out plus VC over R3 also going out. So now we have 3 equations and 3 unknowns, VB, VC, and VA. So we can find all 3 voltages. Once you have the voltages, we can find anything else, right? If you want this current is this, if you want this current is this, and so on. All right? So long as you remember these 4 steps and you go through them carefully, you will be free from mistakes. You can carry out the calculations exactly. All right, very good. Let's look at one more example to see the mechanics of node analysis. Okay, so in this example, we have a current source. So let's call that IX. And then we also have some resistors. So here's one resistor, R1. Here's another resistor, R2. And here's another resistor R3. I'm trying to draw the circuit big so that I have room for all the current annotations that I need to add later. And then we have a dependent current source down here, whose value is 3Vx, and Vx is this voltage here, Vx. And then these all come together like this. Okay, so that's the circuit that we are given. And we want to solve the circuit. All right. Okay, so as usual, we look at the circuit a little bit just to get comfortable. You can see that this current source has a value, and its value happens to be 3 times this voltage. So obviously this 3 has to have a unit, right? It has to be a unit of 1 over resistance, so that when it's multiplied by voltage, it gives us a current. But that's okay, we don't care about that, right? All right, so step by step. Step number 1, find a node that you would call the reference or the ground. Which one? Oh, it doesn't matter, let's pick this one. So this node, this wire, all is just one node. So we're going to call this ground. Okay. All right, step number 2, assign voltages to all the other nodes. So we have a node here. Let's call this a VA. Is this a separate node? No, these are all connected by a piece of wire. So this is just one node here. How about this one? That's another node. Let's call that VB. And then this is another node. Let's call that VC. But something is fishy. Is this really a node? A separate node? No, because you see, it comes down and connects to ground. So no, I don't need to call that a new node. It is ground. So we're going to cross this out and not call it anything. You see, there's a piece of wire connecting this to ground. So this voltage is the same as this voltage, is the same as this voltage. All right? Okay. So then we really have only 2 nodes, VA and VB. Now let's go ahead and find the branch currents, as we said in step number 3. So I'll change the color of my pen, and I identify all the currents. How much is the current through R1? Again, if you rotate it by 90 degrees, you can say the voltage on the left minus the voltage on the right divided by the resistor. So this voltage minus this voltage divided by R1 gives the current in this direction. So that would be VA minus VB over R1. Okay. All right. What other branches do we have? We have a branch here. So how much is the current through R2? Well, the current through R2 is given by this voltage minus this voltage divided by R2. This voltage is 0, it's the ground, so we have only VA. So we can say VA over R2. That's the current through R2. All right. How about the current through R3? The current through R3, for example, let's say I pick the direction to be this way. Then it's this voltage minus this voltage divided by R3. This voltage is VB, this voltage is 0, so it's just VB over R3. So far so good? Yes, I know, in the back of your mind you're worried about this Vx. How does this Vx play in our circuit? Don't worry, we'll get there. For now, we're just following this, the step-by-step procedure for nodal analysis. Okay, so I have found all of the branch currents, and now I can go ahead and write a KCL at each of these nodes. Only 2 nodes, right? The other one is ground. We don't write the KCL at ground because it doesn't give us any new information. All right, so let's write 2 equations here. The first equation is at node A. And which current is coming in? Ix is coming in. These 2 are going out. So we say Ix is equal to VA minus VB over R1 plus, I don't have room here, I'll write it down here, VA, actually I do, VA over R2. So this current coming in is equal to this current plus this current, VA over R2. Okay, we need to write a KCL here as well. So we see that this current is coming in, so we're going to write that as VA minus VB over R1. That current is coming in, and this current is also coming in, right? 3Vx is pointed this way, so plus 3Vx is equal to this current, which is VB over R3. So VB over R3. All right, these are all the KCLs I could write, the independent ones. Okay, that's great. The only issue is that we have two equations and three unknowns, because we have VA, we have VB, and we have Vx. So how do we handle that? Well, we have to look for another equation. We are done with KCL, so we have to look for some sort of KVL. Vx is a voltage, so let's go and see where Vx is. Vx is denoted as shown here, plus here, minus here. That's what the problem has given us, right? They have called Vx positive on this side, negative on this side. But we see that Vx is actually between two nodes, between this node and this node. So if I have this voltage and I have this voltage, Vx will be just the difference between the two. In a sense, I'm applying a KVL. Or if you don't like that, we can try to write a KVL like so. We say this voltage is VB with respect to ground, right? So let's write that as a VB. And that voltage has to be equal to this voltage, which is also from here to ground, right? There's only one little problem here. VB with respect to ground, meaning it means that the high potential is here, the low potential is here, right? When we say VB, that's what we mean. Vx, on the other hand, has its high potential or positive end on the ground terminal. So what really happens is that Vx is equal to minus VB. So we can say this is equal to minus Vx. Now again, if that's not obvious, we can go with our standard KVL. Our standard KVL says, start from here, right? We go up the potential, so we write plus VB. Then go this way, go down, go up the potential, plus Vx. And then we are coming back to the same point, so the result has to be 0. So that's a KVL, and that, of course, gives us the same idea, same number. Okay, so yes, in addition to writing the node analysis equations, if we don't have enough equations, we have to look for something else, which is a KVL somewhere, because we had this dependence in this particular example. All right, so now that we have three equations and three unknowns, we can find VA, VB, Vx, and everything else. We have seen resistors in our circuits before, and they are generally constant. But it is possible to use resistors whose value actually depends on something in the environment. One example is what we call a flex sensor. It's a long strip with two terminals, so we can measure the resistance between these terminals. And if we bend this strip, the resistance actually changes, and it changes significantly. So if you hold it between our fingers and bend it, we have a different value. So the first question is, how do I measure this change in resistance? That should be pretty straightforward, right? So let's build a simple voltage divider, as we have seen in the past, and connect it to a battery. So we know that the output voltage here is given by the battery voltage times this resistance divided by the sum of the two. So what we see is that if the flex resistance changes, so does this output voltage, and that's how we can measure it. Now, what can we do with this device? What kind of application can you think of? Well, from this website, from University of British Columbia, you can see that they use these flex sensors in a glove. And they attach the outputs of these flex sensors to a simple Arduino. So as we wear this glove and we flex our fingers in different forms, we can detect how much each finger has bent and what we can do with it, right? So that becomes a very interesting scenario that can find a wide range of applications. So in fact, on this website, they give us a bunch of examples. They say, for example, you can communicate with this glove for people who have disabilities. For example, they are mute or deaf. So they can use this to talk to other people, so to speak. Then they also say for virtual training. So we might be able to use this for training in a situation where the actual training would be dangerous. So this can emulate that training system. And for example, they can also study physiology. For example, if we have some injuries, for example, athletics, in athletic training, people have incurred injuries, we can use this glove to see how much they can bend their fingers, what kind of pain they experience, and so on. So you can see that a very simple device has so many applications. Isn't that beautiful? Okay, good. Let's move on to a difficulty that we face. So I would like to show you another example, and then we'll see why we have a problem. So let's go to the next page and see what we get here. Okay, let's look at this example. I have something like this. So let's see, I have a resistor R1, a voltage source, which we will call Vx. Then we have another resistor R2, another resistor R3, and another resistor R4. And then these are all connected like so. Okay, so we're given this example, and this example differs from the previous ones in that it has a voltage source. I deliberately avoided using voltage sources in the previous examples because a voltage source gives us some difficulty and we have to address that. All right, so no problem, we follow the steps, right? Step number one, select a reference point. So let's say this is our ground. Again, doesn't matter which one, but this is fine. All right, step number two, go ahead and assign a voltage to all the other nodes. So here's a node, I call that VA. Here's a node, I'll call that VB. And here's another node, we call that VC. Okay, so it looks like there are three nodes, so each of them merits a voltage, a name. Okay, and then while we are here in step number three, we will try to write the current through every branch on the schematic. So let's do that. I'll change the color of my pen and try to do that. Okay, how much is the current through R1? Well, this voltage minus this voltage divided by R1, right? So that's VA over R1. That's great. How much is the current through R2? This voltage minus this voltage divided by R2, so VB over R2. How much is the current through R3? Let's say going from left to right. So the voltage on the left minus the voltage on the right divided by the resistor value. So I don't have room there, I'll just move it over here. So that's VB minus VC over R3. Okay, and finally, how much is the current through R4? This voltage minus this voltage divided by R4, so that current is VC minus 0, because we have ground, divided by R4. All right, looks like we have found all the currents through all the branches. Not quite, but let's just proceed and see what happens. Okay, so let's start writing some KCLs. Now that we have found all the currents, our next step is to write KCLs so that we can solve those equations and find the unknowns. Okay, well, I'm going to start from this side because it's simpler. Let's write a KCL at node C. What do we have there? Well, I have a current going this way and a current coming in. So the current coming in is VB minus VC over R3, and that has to be equal to VC over R4. So that's easy enough. VB minus VC over R3 is equal to VC over R4. Okay, that's great. Now let's move on to this node, node B. How do I write the KCL here? All right, this current is leaving and this current is leaving, so that's great. So let's write those here. We have VB minus VC over R3. This current is coming out of the node, and so is this current. So plus VB over R2. What am I missing? I'm missing a current here, which might be, for example, going this way. How much is that current? I don't know. That current cannot be found from what we've done before. We continue to apply Ohm's law to every one of these resistors. A voltage source does not satisfy Ohm's law, so I cannot write anything about the current here, right? So what do I have to do? Well, let's just call it something and see what happens. So let's call this IX. Okay? I don't know how much IX is, and because the voltage source does not satisfy Ohm's law, I cannot write the relationship between Vx and Ix. All right, so we just write it as Ix. So far, so good? Okay, so if this current is Ix, this current is also Ix, right? Because it's, current cannot disappear. Whatever flows from this side ends up from the other side. So let's write the KCL at this node as well. So we're going to write this current is leaving and this current is also leaving. So they have to add up to 0. So we have Ix, which is leaving, plus a VA over R1, which is also leaving. And there's nothing coming into the circuit, into the node. So we have the sum of these two equals 0. Okay, so am I in good shape in terms of solving these equations? No, not really. How many unknowns do we have? It seems that we have VA, VB, and VC. 3 unknowns, plus IX, because I introduced that here. I have 4 unknowns and 3 equations. So we have a problem, right? So the problem arises because I introduced this IX, because there was no other way to find this current, to call this current, right? This current doesn't come from Ohm's law, so it just has to be something, some unknown. So the difficulty here is that we have 3 equations and 4 unknowns. So we cannot solve the circuit yet. Okay, so how do we handle this? Well, we're going to take 2 additional steps, and the steps will be as follows. So take 2 additional steps. This happens anytime we have a voltage source in our circuit. All right? Okay, in step number, let's call this step number 5, right? We had 4 steps already, so step 5. You say write, or maybe I should do this, form a supernode by merging the nodes on the 2 sides of the voltage source. Okay, this is actually pretty simple. This sounds a little abstract, but it's pretty simple. So let me show you what that means. I'm trying to avoid this IX here, right? Because IX just gave us a new equation, a new unknown, so it didn't really help. So we don't write Ix, right? We just say, well, if you look at the circuit carefully, what I can also say, in fact, I can say that for any circuit, but it's useful to say it here. What I can also say is that if I place this part of the circuit in a box, so this part of the circuit includes the voltage source and the two nodes that are attached to it, right? If I put this whole thing in a box, I see that that box has a bunch of wires going in and coming out of it, right? So we have a wire coming out here, we have a wire coming out here, a wire coming out here. And we know that as far as these wires and these currents are concerned, we still have to have charge conservation, meaning KCL still has to hold. So if you take any circuit and there are a bunch of wires coming out of it, and we have some currents, right? The algebraic sum of these currents still has to be zero, because it's like an intersection in the city. If you have cars coming in and cars going out, the sum of all these currents or flow of cars has to be zero, because cars cannot disappear in the intersection, or they cannot be created in the intersection. So we will put the voltage source, which is causing trouble for us, and its two nodes in one box. And now this box has a bunch of wires coming out of it. We're going to write a KCL for that box, not for the voltage source anymore. So write a KCL for this box, which is called a supernode. So a supernode is just the result of merging two nodes that are on the two sides of the voltage source. I put merging in quotation marks because not really, not like shorting the nodes or anything. We're just merging them in our mind. So can I write a KCL for this box? Sure. How much is this current? This current coming out of the box is VA over R1. How much is this one? Is this also coming out? So plus VB over R2. And then something else is coming out right here. So that's VB minus VC over R3. And the result is 0 because we don't have any current going in. All of the currents that we have shown on the circuit happen to be coming out of this green box. Okay? I can write this equation because KCL must hold for any system. Right? Charge cannot disappear, so all of these currents have to add up to 0. Okay, so now if you can see, here's the situation. I have one equation here. That's great. I have another equation here. That's great. We don't have Ix in any of these equations. So we have two equations, but three unknowns. Why? Well, because when I merged these two nodes, I removed one KCL. Remember, we have one KCL per node. So originally we were hoping to have three KCLs because we had three nodes. But because I merged these two nodes, I lost one KCL. And that requires that we go to one more step. And the next step, step number 6, is to write a KVL involving the voltage source. Remember the voltage source that's giving us trouble, right? We're going to write a KVL involving that voltage source. And that's pretty simple. All we need to do is we write, we have over here, we have VA, and then here we have VB. And the difference between these two is this voltage source Vx. So all I need to say is VA plus Vx is equal to VB. Okay, you have to be careful with the signs here. How do I know that? Again, VA is like this, right? Positive here, negative here. So going up the potential, going up the potential, going down the potential for VB. But anyway, you have to think about that, but that's the result that we get. Okay, so now that I have this new equation, I have made up for the missing equation. Because we said we have 1, 2 equations, but we have 3 unknowns, VA, VB, and VC. But this voltage source allows us to create a relationship between VA and VB. So with this equation and these two equations, now I have three equations and I can solve everything. This is the procedure for solving circuits that have voltage sources in them. And the concept of supernode comes in handy because it allows us to write a KCL without introducing a new current here. All right, this concludes today's lecture. Next time we'll come back and practice with this idea. I'll see you next time.